Okay, Chapter 5, Section 2. Here we're going to look at the trigonometric functions, the values of trigonometric functions, and the fundamental identities. Okay. So a function is a rule that assigns to each number another number, right? This is general definition of what a function is. So we're just going to define these new functions that are the sine function and the cosine function and the others. Trigonometric functions. Okay, so far we've been working with a unit circle, and then we defined this t value to be the distance along the curvature, along the circumference of the unit circle. So t, if it's a positive number, heads in this direction, counterclockwise. If t is negative, then it goes in a clockwise direction. Remember that the circumference of the entire thing is 2 pi. So if t equals to pi, or approximately 3.14 units, then it goes from there to there, right? If t equals half a pi, it'll go from there to there, right? Okay, so wherever t lands, it'll land out on one point on the unit circle. We call that the reference point, or the terminal point, and then we can label it x comma y, or so, right? So whatever that point is, it must be a point that satisfies the equation for a unit circle, x squared plus y squared equals to 1. Good. So some of the obvious ones we can find. So when t equals to pi, it goes all the way over here. And then that terminal point is the point -1 comma 0. When t equals to 2 pi, then it goes one complete lap around. So then the ordered pair at the end of that is 1 comma 0. Right, so some of them are pretty obvious. Now, a lot of this seems really familiar from the introduction to trigonometry from Chapter 6 we've already done. So in Chapter 6, we were dealing with angles. So remember from Chapter 6, we had an angle. And so we had, say we had this angle there, and we had theta there, and it was written in standard form or standard position along the y-axis. So here is one angle, and then what we would do is we would bring it down here, form a right triangle. Therefore, this point right there was the point x comma y. And then this distance over here would be the distance x. Let's put it in that. That would mean that this distance is the distance y, and this distance is the distance x. Right? So we can figure out what that radius is. Just call it r. Good. And so it must be true that x squared plus y squared equals r squared. Right? Pythagorean theorem. Okay. And so we saw, or we defined the sine function, sine of theta, to be equivalent to y over r. Y over r. And cosine of theta, to be equal to x over r. Good. Okay, now we also saw that this relationship is true no matter how big these values are. So we can make a really big triangle like that one, or we can make a tiny triangle like this one, right? And then find whatever this distance is, x prime and y prime. It's supposed to be an x prime. So this distance could be x prime, this could be y prime. It turns out that this is going to be the same. Cosine of theta, it's the same angle, is equal to x prime over, and then this little distance here would be r prime. X prime over r prime. And cosine of theta is equal to y prime over r prime. Right? So it doesn't matter whether you make a small triangle or a bigger triangle. It doesn't matter. The division of its opposite, the length of its opposite side divided by its hypotenuse, the length of its hypotenuse, is going to give you the same result. Good. So since you can make any triangle, there exists a special triangle, the triangle that happens to have radius 1. So if we, I don't know what color should we, how about purples? We're going to play with purples. So there, since you can choose any value along this curvature, we can happen to pick the one that has a distance of 1. So therefore, it's a value that's on the unit circle. So as this kind of comes this way, and this, whoa, let's pretend that's a nice pretty circle. This could be the unit circle. Good. And so this point right there can be used to draw a triangle. Comes this way, comes that way, and now we have a new value there. That's the height there, a new x. And so we can say that it equals the same thing. It just so happens that the radius is 1. So in this case, cosine of theta is equal to this y, let's call it y hat. Y hat over its radius, which just happens to be 1. Oops, this is cosine, so this is x. X hat over the radius, which just happens to be 1, right? So this distance from there to there is x hat. Okay. And then sine of theta is equal to y hat over 1. And since it's just over 1, we can just say it's equal to cosine of hat. Cosine of theta equals to x hat, and sine of theta equals to y hat. Any questions at all so far? So that looks really messy, so I'm just going to take out the purple part and redraw it over here. And so if I have the unit circle, y, x, then a point on the unit circle is this, some x comma y value there. It's on the unit circle, so we know that that distance is 1. And we know that this height here is the y value. And this is the x value. To make it match what we did up there, then this would be x hat, y hat. This would be y hat, x hat. Good. And then we'd have some angle value theta there. Good. Okay, so now in this chapter, this was what we did back in chapter 6. Now in this chapter, all they're doing is defining that ordered pair value to be the distance along the unit circle tracked by some t value. Good. But we know that when we define it in terms of radians, this angle in radians is equivalent to that distance in the unit circle. Right? So pointing out that this has to be the unit circle. So theta, angle theta in radians is defined as t, the distance subtended along the arc by this angle. Right? That's what it is. That's the definition of it. Does that make sense? So, for instance, if t was equal to 1.2 radians, whatever units that is, it could be inches, feet, meters, it doesn't matter. If you go along this curvature 1.2 units, then we define this angle to be 1.2 radians. Oops, I shouldn't have put radians here. If t equals, this is a distance. This is a distance. a distance of 1.2 units along this curvature, then by definition, we define this angle, theta, equals 1.2 radians. Any questions? No? 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 Okay, so for that reason, we simply define the x-coordinate along the unit circle to be equal to the cosine function of t, and the y-coordinate to be the sine value of t. So we have, again, we have this unit circle, and we're going to define a terminal point defined by some value t. I know that in chapter 6 that means that we're talking about angle t in radians, but in this chapter we're only talking about the distance traveled along the unit circle. Unit circle. Good. So let t be any real number and let p of t be the terminal point, right? So p equal to x comma y be the terminal point. Let's put it in blue. Say this point right there would be the terminal point, x comma y, that is described by this distance t along the curvature. Then we're simply going to define the x-coordinate of that terminal point to be cosine of t, and the y-coordinate to be sine of t. So remember, there's an introduction to trigonometry, and I think this is a terrible introduction to trigonometry. It's just kind of defined to be that without really explaining anything else, right? So if this is for someone that, you know, has been introduced to the field of trigonometry, has never seen this function before, doesn't know what it is in any other context, I think this is a terrible way to explain it, but it is a way to do it. Okay, any questions so far? No. And so, of course, that means that if you did create that right triangle that drops down here and comes across that way, then the x value would be this. So this would be cosine of t. Oops, the other way around. This would be sine of t, and this would be cosine of t. Right, so this distance here, this is the cosine of t, whereas this distance here, the height of this, would be the sine of t. So in the right triangle form, the heights are t, and the base of this triangle is cosine of t. Good. So if it was a t value that stretched all the way out into quadrant 3, say that the t value went all the way out to here, then we would end up with a triangle that comes this way. Oops, let's put it in green again. Triangle that comes out to here and up to there, like that. And then again, this would be cosine of t, comma sine of t. Right? This is assuming that this is a t value. Let's change the color. This is a t value that stretches from here and goes all the way out to here. Say this is the t value that stretches all the way out to here into quadrant 3. Then this point would be the terminal point, and it would be cosine t sine t. Good. And so this right here would be cosine of t. Cosine of t would be this, so I can tell that the answer would be negative. And then this would be sine of t, and again I can tell that the answer would be negative. Right? T would be a number such that when I plug it into sine function, the output would be negative. Good? Questions? No? Okay, so from that we can get the other ones. Tangent of t is defined to be y over x. And then cosecant of t is 1 over y. Be careful not to divide by 0. Secant of t is equal to 1 over x. Be careful not to divide by 0. And then cotangent of t is equal to x over y. Good? Okay, so this is where we are so far. Let's find the 6 trigonometric functions for each of these values. So when they give me t equals to pi over 3, that's a distance along the curvature of the unit circle. And we know that from here all the way out to here is pi. So from here out to there is half a pi. And so we want to take this distance from here all the way out to here and divide it into 3 equal portions, and we want 1/3 of that, 1/3 of pi. So it lands somewhere there, right, in quadrant 1. And so according to this description of what a sine and a cosine function are, all we have to do is take the x and the y coordinates from that terminal point, and that's how we define the x. That's how we define all the trigonometric functions. Good. And in chapter 5, how did we find these values? Remember that we used just algebra and geometry to figure them out and to create this table. Right? All of this stems from knowing that the point is on the unit circle, therefore it must obey the equation of a unit circle, x squared plus y squared equals to 1. So knowing that fact, that equation, and a little bit of geometry about halves and thirds and various things that we can do to figure out how to get that ordered pair. We solved it for the easier case of pi over 4 yesterday. Good. Okay, so now once we identify that this is pi over 3, we go over to our table, and let's zoom in a little bit to this table. We go over to our table from yesterday, and we see that, oh, okay, that ordered pair is 1/2 comma root 3 over 2. So simply by looking at that ordered pair, I can tell that cosine of pi over 3 is the x-coordinate, 1/2. Sine of pi over 3 is the y-coordinate, which is this one. And then I can find all the other trigonometric functions that way. Okay, so sine of pi over 3 is root 3 over 2. Cosine of pi over 3 is 1/2. And then tangent of pi over 3 is y over x. So root 3 over 2 divided by 1/2. That simplifies to root 3. And then we can find the others in the same way. Any questions about this? No? No? If you're feeling a little uneasy about this, I think it's appropriate because it's kind of a weird thing that we found this table and then now we're just simply defining the x-coordinate to be this cosine function and the y-coordinate to be this sine function without really truly giving like a really good understanding, I think, of what it means, what the sine and the cosine function mean. But at any rate, we can just follow the rules here and play along. What about the other one? We want to find all the trig functions associated with pi over 2. Well, that's easy since pi over 2 is just going to be from here to there, right? Pi over 2. And so therefore we have this as the ordered pair there, 0, 1. That one was an easy one to get. And from there we can say that cosine of pi over 2 is 0, sine of pi over 2 is 1, and then all the other ones are found in similar respect. So we have pi over 2 goes to 0, 1. And then we can get all the other ones this way, and we have to be careful not to accidentally divide by 0. Right? So note that tangent of pi over 2 is going to be undefined. Good. And so this table has several of those values for some of the key angles. 0, pi over 6, pi over 4, pi over 3, pi over 2. And like I just said, tangent is going to be undefined, because tangent is defined as y over x, or sine of t over cosine of t, and cosine of t is 0 at that point, therefore you'd be dividing by 0, it's undefined. Any questions at all at this point? No? No. Okay, so you could memorize this whole table here, or really just these 3 key points right in here in quadrant 1. If you memorize those, you should be able to figure out everything else, right? The cosine is the x-coordinate, the sine is the y-coordinate, tangent is sine over cosine, and then you can figure out all the other ones from there, secant, cosecant, cotangent. And that's all in quadrant 1. And then you can make extensions to quadrants 2, 3, and 4. Questions? Let's move on to the values of trigonometric functions. I'm skipping some of this. A lot of this is covered in your book. And so for the interest of time, I'm just moving along to the more interesting things. Again, memorizing where the functions are positive and when they're negative. If you understand quadrant 1 really well and how it relates to the other quadrants, then I don't think you have to blindly memorize what this is without really, understanding it. Okay, so if we're evaluating trigonometric functions for any real number, not just quadrant 1, then we need to find the reference number. We need to find t bar. We need to figure out what quadrant it's in to be able to do that well. Then we're going to reference it back to something in quadrant 1, so it's related to something in quadrant 1, except potentially for a plus or minus somewhere along the way. And then we'll be able to find all the trigonometric values of the one we're looking for. Okay, so let's practice that. I think you'll see what I mean. So here's some examples. Number 1, cosine of 2 pi over 3. Part A. Solve part A. Okay, so the first thing we have to do is think about where is 2 pi over 3 in relation to which quadrant it's in, so we can find the reference value. I would recommend converting the 2 pi over 3 into 2/3 pi. So from here it's clear that it is less than 1 whole pi, since this fraction is less than 1, and it's bigger than half, since it's 2/3 is about 0.67, right? So it's approximately 0.67 pi. Okay, so this is going to be in quadrant 2. Good. I can do like a little drawing to approximate it. That's really ugly, but whatever. It'll get the job done. And then, so we're talking about some t value like this. That's equal to 2 pi over 3. So then the reference value is going to be this one, the rest of the distance along the unit circle until you get to the x-axis. This is y, this is x, and this is t bar. Okay, so t bar must be equal to pi minus this number. T bar then equals pi minus 2 pi over 3, which means that t bar is equal to 3 pi minus 2 pi over 3, or t bar equals to pi over 3. Good. Pi over 3. Okay, so now what we do is we think about the value pi over 3 over in quadrant 1. Consider the value over here in quadrant 1, t bar equal to pi over 3 over in quadrant 1. it ends up with some terminal value in quadrant 1, and this is some ordered pair, and again we just get this from our table. So we just have our table right up here. Let's look at it. So this is going to be 1/2, comma, root 3 over 2 in quadrant 1. Good. So from that, I can deduce that the x-coordinate in relation to this one must be negative, and the y-coordinate is positive. So from that, I can conclude that this point must be the point negative 1/2, comma, positive root 3 over 2. Good. And from the definition of things, I can finally get to my final answer. We defined the cosine function to be the x-coordinate of my terminal point. So for part A, all I have to do now is say, well, here it is. This has to be my answer. So cosine of 2 pi over 3 must be equal to negative 1/2. Any questions about this? No? No questions? Okay, same thing for part B. We have tangent of negative pi over 3. So that's obviously going to be in quadrant 4, since 1/3 of pi, so pi over 3, is equal to 1/3 pi, which is equal to 0.33, or approximately 0.33 pi. So it's less than half a pi, and it's negative, so it's going in the clockwise direction. So we can do a quick little sketch. Here's a unit circle. That's really ugly, but it'll get the job done. And it'll come over here, and so we got to go this way. And this is t equals to negative pi over 3. Good. And so I'm going to say that that's equivalent to, kind of consider, man, this is a really ugly unit circle, but you know, that's supposed to be the unit circle. I can't live with it. It's going to erase the whole thing, isn't it? Thought so. Okay. Okay, so here is a better unit circle. Yay. Okay, so now we're going to consider another t value that comes this way, like this, where this one is positive pi over 3. Good. The reference, the terminal point here, just like up there, is the point 1/2, comma, root 3 over 2. And so in relation to, or referencing that, it must be the same x-coordinate, but the opposite sign for the y-coordinate. So from that must mean that this is positive 1/2, comma, negative root 3 over 2. And now I'm ready to answer the questions, right? From the definition in chapter 5 of what a cosine function is, cosine is just equal to x, and sine is just equal to this. So it didn't ask me for this, but I'm going to use it anyway. So that must mean that cosine of negative pi over 3 is equivalent to positive 1/2. And it must mean that sine of negative pi over 3 is equal to negative root 3 over 2. And remember that tangent of negative pi over 3 is equal to sine of negative pi over 3 divided by cosine of negative pi over 3. Right? Tangent is equal to sine over cosine. So this is going to be equal to negative root 3 over 2 divided by positive 1/2. Right? So this reduces to Tangent of negative pi over 3 then becomes equal to negative root 3. Right? And that was the question they wanted. Find tangent of negative pi over 3. Any questions? No? No? Okay, so make sure that you learn how to do it this way, because when test 3 comes along and I ask questions from this chapter, you need to demonstrate that you're doing it by the methods provided in this chapter. So you can't just jump to the conclusion that tangent of negative pi over 3 equals to negative root 3, or even worse, someone that just submits the decimal approximation. What is root 3? Root 3 is 0.8, no, 1.7. Right? If someone just gives me the answer from this, tangent of negative pi over 3 equals to 1.7, negative 1.732, and just kind of leaves it at that, then I just have to assume you just used technology to find this, and you didn't really use the tools or the reasoning from chapter 5. So make sure you practice doing it this way. You got to draw a unit circle. You got to find the reference length t. Oops, this is supposed to be t bar. You have to find t bar. I want a drawing that shows where the original t is and where t bar is in relation to quadrant 1, and then find the terminal point in quadrant 1, and then how that relates to the terminal point of t, and then some sort of indication of how you got it from there. Any questions about that? So this will receive no credit. No credit. And the purpose of math is very little of it has to do with finding answers. Right? It's about the process. Okay. 19 pi over 4. Now I've got to deal with 19 pi over 4 for part C. Part C. Find sine of 19 pi over 4. Okay, so we got to deal with that value. So if t equals to 19 pi over 4, first thing I noticed that is if we turn this into a decimal, it goes into it 4 and 3/4, 4 and 3/4 as a mixed number, pi, which is equal to 4.75 pi's. And remembering that 2 pi equals 1 lap, therefore 4 pi must be equal to 2 laps complete around it, then that means that 0.75 must be a coterminal reference value. So t equaling to 19.4 is going to be equal to t equals to 0.75 pi, or 3/4 pi, 3 pi over 4. Okay, now you can get that simply because I figured take away 4 from here to get to 0.75, which gives me 0.75, and I can turn it into that. Or I can actually do a little bit of work here and do, or I could do 19 pi over 4 and subtract 4 pi, right? Get a common denominator. It's going to be that 4, so times 4 over 4, which gets me to 16. That would be 19 pi minus 16 pi over 4, and that's how we get 3 pi over 4. Okay, so now, working with 3 pi over 4, 3 pi over 4, 0.75 pi is bigger than half, less than 1. That's going to be in quadrant 2. Okay, so here's my unit circle. Y, here's X. And so now I want to work with this one. Let's go over here. Okay, stops there, somewhere around there. And this is going to be equivalent to the one we wanted to work with that does one complete lap, two complete laps, and then some, right? So it ends up giving you the exact same terminal point. And so that terminal point is going to be important to figure out. And to do that, I need to find the t-bar value. The t-bar value, because it's in quadrant 2, is going to turn out to be pi minus this value. Right? Another way to look at it is that if this is 0.75 pi, 3/4 pi, then this must be the rest of it, 0.25 pi, or just pi over 4. Good. So I would say that t bar equals to pi minus 3 pi over 4. Common denominator is that 4. So multiply by 4 over 4, we get 4 pi minus 3 pi gives you pi over 4. Pi over 4. Good. All right, so now that we're armed with that reference value, we can come back over here and consider unit circle going back to quadrant 1. In Q1, there is a t value that goes from there to there. This is t hat. Oops, sorry, not t hat, t bar. And it gives you a terminal point. And if we look at our table, this terminal point is root 2 over 2, comma, root 2 over 2 in quadrant 1. Good. So based on that, we know that the one we must be working with, which kind of extends out to there, that one must be the point negative root 2 over 2, comma, root 2 over 2. The x-coordinate must be negative. The y-coordinate stays positive. Good. Any questions? All right, so let's piece it all together. We know that sine of 19 pi over 4 must be equivalent to sine of 3 pi over 4, right? Because they're coterminal. And then this is equivalent to the y-coordinate of the terminal point, which is equal to root 2 over 2. Any questions about that? No? Maybe? Sort of? Kind of? Maybe? Sort of? Kind of? So here's the same thing I did, just some nicer graphics. The first one was 2 pi over 3, so that leads you to quadrant 2. That extra little gap is pi over 3. Putting it into a value in quadrant 1 gets you the ordered pair. And so we have to connect it back to quadrant 2, and we get an answer of negative 1/2. Cosine of 2 pi over 3 equals to negative 1/2. Good. The second one was negative pi over 3. So we use the reference value of pi over 3. And so we got negative root 3 as our final answer. And then finally this last one. Started off with 19 pi over 4, that's 2 laps and then some. That ends up giving you another coterminal value with 3 pi over 4. That gives you a reference value of pi over 4. And then from our table we can see that's just going to be root 2 over 2. And so we get that. Any questions? No? Okay, so we can work with some basic values of t, but if t was anything else, anything that doesn't fit into one of our standard known values, then we just have to use our calculator and make sure that it's in radian mode. Just reminding you of that. Good. Let's see. So practice using our calculator. I think we have enough practice for that, right? We don't need that. And okay, well, let's just make sure that people know how to put in radians. So let's get our calculator and just type in these guys real quick and make sure we confirm that we're getting the same results. Okay, so we want to go over to mode, and right down here, make sure you change it over to radians. Okay, remember by default, if it doesn't have that little open circle thing here, if it doesn't say degrees, then by default we assume it's radians. So hit enter, and then quit out of here, clear. Okay, so sine of 2.2, close parentheses, equals to that. And cosine of 1.1 equals that. Yep. Now, we don't have a cotangent button, but we do have a tangent button, and we know that cotangent is 1 over tangent. So 1 divided by tangent of 28 gives you that number. And same with cosecant. We don't have a cosecant button, but we easily know that that's 1 over sine. So 1 divided by sine of 0.98 gives us the same result. Okay, good. Any questions? No. Okay, so let's take a look at a relationship that happens in a case like this. So one of the examples we saw before had negative 3 pi over 4, and then we made that reference or that reference value compare it to positive 3 pi over 4, and so we had this sort of a relationship. So when we have this sort of a relationship, notice that the x-coordinate stays the same, and then the y-coordinate just changes by a minus sign. Good. So this is indicating that these statements are true. Right, looking at the x-coordinate stays the same, right? So this x-coordinate right in there is cosine of t, and this one is sine of t. Whereas here, this whole thing, this guy right here is cosine of negative t, right? That's this one. And then the whole thing, the negative y, the whole thing, negative y, is the result of sine of negative t. Good. So sine of negative t equals negative y, and then the y by itself was equal to sine of positive t. Good. So we can combine these two things and say that sine of negative t, oh, let's not put it in red. We can say that sine of negative t is equivalent to negative sine of t. Right? So what this is saying, for example, putting it back in terms of degrees, sine of negative, or let's stick to radians, sine of negative, what do I want to say, about pi over 3. Sine of negative pi over 3 is equal to negative 1 times sine of positive pi over 3. Now, some people might choose to look at this and think that what we've done is factored out a minus 1, but that's not what we've done, although it kind of looks like that. That's not what it is, though. We're simply stating that when you input this negative angle, it's equivalent to finding the positive angle, sine of the positive angle, times a negative 1. Right? In terms of degrees, we can say that this is saying that sine of negative 70 degrees is equivalent to -1 times sine of positive 70 degrees. Good. So this becomes a really useful shortcut, because if you don't want to find the sign of a negative number, all you have to do is find sine of its positive counterpart and then multiply the whole thing by -1. Good. And even more useful is this one. We're indicating that cosine of t equals x, but cosine of negative t also equals x. The x coordinate stays the same. So we get this statement here, and so we get to match those two together and say that cosine of negative t equals cosine of positive t. Good. Another useful shortcut, right? So we have two really useful shortcuts. This one, right, that if we have a minus in there, we can simply find sine of positive t multiplied by -1. And then this one, an even better, simpler shortcut. This one is saying that cosine of a negative angle is equal to cosine of its positive counterpart. So in other words, cosine of negative 30 degrees, if you're trying to figure out what is cosine of negative 30 degrees, well, don't worry about the negative. This is the exact same thing as cosine of positive 30 degrees. Just ignore the negative. Good. Questions, 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 questions? And then finally, the other property, tangent of negative t is equal to negative y over x. As we saw before, the negative y is really the same thing as, wait, why do we have a, this is cosine, this is sine. Cosine gives you negative y, oh, it's over here, duh. My eyes were deceiving me here. So negative y over x, which is negative y over x. And so this ends up giving you tangent of negative t equals to negative tangent of t. Same as the sine one. It almost looks like you can factor out the negative, but it's not quite factoring out a negative. It's just that it's equivalent to its positive counterpart times -1. Good. So skipping this middle part, we'd end up with tangent of negative t is equal to -1 times tangent of positive t. Any questions about these properties? No? No? So these equations show that sine and tangent are odd. If you remember back when we defined what an odd function was and what an even function was, then this satisfies, cosine satisfies that it's even, and sine and tangent show that it's odd. So back from a previous chapter, I forgot where, we looked at sine of a function that's even. So even functions are functions where, let's say we have f of x. If we replace, so given f of x, if I replace the x with some a value, and that's equal to f of negative a, right? Whether you plug in a positive or a negative, that it gives you the same result, that's when we get an even function. Good. And an odd function, right? So given some function, let's get away from that. Given some function g of x, if I plug in a negative a, and that's almost equal to plugging in a positive, except that there's a minus out in front, then we'd say that this one's an odd function, right? So cosine satisfies that it's even. Evaluating cosine at a negative angle is equivalent to evaluating cosine at a positive angle. Good. And then tangent and sine are odd functions. Good. Questions, questions, questions? Odd and odd. And remember, when we graph an even function, it's a reflection about the y-axis. And when we graph an odd function, it means that the reflection about the x-axis is equal to the reflection about the y-axis. Good. Okay, so here's a nice little table of all those properties. Sine of negative t equals to negative sine of t. Cosine of negative t equals to cosine of t. And tangent of negative t equals to negative tangent of t. And then their counterparts, which are equivalent. Good, 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 good. Okay, so we can use some of those shortcuts to find these things. According to this, in order to find sine of negative pi over 6, sine of negative pi over 6, is equal to negative 1 times sine of positive pi over 6. That's what that's saying. Good. And now pi over 6, well, if we remember our basic values from our table, pi over 6 is going to be like over here. And the terminal point associated with pi over 6 is equal to root 3 over 2, comma 1/2. And so this is just going to be equal to negative 1 times the y-coordinate of the terminal point. So this one is going to be pi over 6 there. So this one's sine of pi over 6. Good. Questions, 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 questions? All right, cosine of negative pi over 4. So according to our property, cosine of negative pi over 4 is simply equal to cosine of positive pi over 4. No changes, right? That's what this is saying. Cosine of negative t is equal to cosine of t. So cosine of negative pi over 4 is the same thing as just cosine of pi over 4. And again, if we go back to our unit circle, the first quadrant, when t was equal to pi over 4, the terminal point associated with it is root 2 over 2, comma root 2 over 2. And so the x-coordinate is just the cosine of that value. Right? This is where t equals to pi over 4. So this must be cosine of pi over 4 equals that first value there. So this is just going to be equal to root 2 over 2. Any questions? No? No questions, no questions, no questions. Okay, that's what they did there. Fundamental identities, we've been working with these before. They're defined in the same similar way. If cosine of t equals to 3/5 and t is in quadrant 4, okay. If cosine of t equals to 3/5 and t is in quadrant 4, find the value of the trigonometric values of t. So let's see, we have a unit circle, and then we have a t value that goes into quadrant 4. So it's something that goes all the way around and ends up somewhere in the quadrant 4, like this. Okay, so we end up with some point there, some terminal point x comma y. And we know that cosine of this is equal to 3/5, so it must mean that this must be 3/5. Okay, so now how do we find this value over here? Well, it must be true that because it's the unit circle, it satisfies, right, this is the unit circle, circle, circle. Okay, so it must satisfy the equation x squared plus y squared equals what? Right, this is y up there, this is x over here. So if we replace it there, 3/5 squared plus y must be 1. Then this must be 9/25 plus y equals to 1. So y equals to 1 minus 9/25. Sorry, squared. So y squared equals to 25/25, common denominator. Which gives you 16/25. So y equals to plus or minus the square root of 16/25, or y equals to plus or minus 4/5. Good, so it's not that it's both answers. Going back to here, we have to decide for ourselves. And I can see that in quadrant 4, the x-coordinate should be positive, and the y-coordinate should be negative. And that's how I conclude that this number right here must be the number negative 4/5. Good. Any questions about that? And now that I have my x and y coordinate, that's the terminal point associated with a t-value, with an unknown t-value. Right? This is the t-value that takes you from there all the way around to there. Now I can find that cosine of t must be this, sine of t must be this, tangent of t must be this one divided by that one. Good, so we can find them all that way. Let's write them down, or, well, here they are. Sine of t is just this guy, so it's going to be negative 4/5. Cosine of t is going to be this guy, 3/5, right? Tangent of t is sine over cosine, which is y over x, so it's going to be negative 4/5 over 3/5, which reduces to negative 4/3. And then if we want to find cosecant, cotangent, secant, then it's just to flip these around. So sine of t equals to negative 4/5, then cosecant of t must be equal to negative 5/4. Good. Any questions? No? No? No questions? No questions? No questions? No questions? No questions? Okay, so Chapter 5, Section 3, Trigonometric Graphs. And again, I know we've already worked with the general shape of the sine and cosine function, but we're reintroducing it one more time. So in this section, we're going to graph the sine and cosine function, and then think about how those graphs can be transformed using the same properties we already learned in a previous chapter about transformation of functions. You know, what happens when you add a constant, what happens when you multiply by a constant, stuff like that. Okay, so as far as the basic graph of a sine and cosine function, okay, so there's a few things we already know. We know that for both sine and cosine, if we add a multiple of 2 pi, we end up back at the same ordered pair, right? So on the unit circle, remember that in Chapter 5, we're defining let's go back over here. Remember that on the unit circle, here's our unit circle. Oops, that's really ugly. Whoa, how'd that happen? I'm all the way down to the bottom of the page. Okay, so we know that on the unit circle, something like this, here is this, here goes that. If we have some t value that goes, say, from the start to there, so we have some t value that does this and goes like that, that ends in some terminal point there. I don't know, let's call it a comma b, some terminal point that belongs right there, and it's associated with t, right? Therefore, if we want to define what is cosine of t, well, it's that x-coordinate. And what is sine of t? Well, it's that y-coordinate, right? So the y-coordinate of that terminal point is the sine, the x-coordinate is the cosine value. But then if we add another lap to this, another multiple of 2 pi, so we get this t value, t, and we add to it 2 pi, whatever t is, plus another 2 pi, let's say we call that t hat is equal to that, then it's going to be the same as going this, we get there, and then we're going to do one more full rotation. We go all the way around, and we end up in the exact same spot, right? Which means we're going to get the exact same values. Good. So this is saying that we're going to end up with the same thing. So cosine of t hat is going to be the same as cosine of t, which gives us the a value, and we're going to get that sine of t hat is the same as sine of t. Good. Okay, so if we piece that together, cosine of t is equal to cosine of t hat, where t hat was defined to be that. Cosine of t plus 2 pi is equal to cosine of t. Good. And that's true whether I do one lap or another lap, so make it 4 pi, so add 4 pi or add 6 pi, right? I can add extra laps and I end up at the same terminal point no matter what. Good, 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 good. So that's where this little statement comes in, this little blue box here. Sine of t plus 2 pi is just equal to sine of t. And cosine of t plus 2 pi is just equal to cosine of t. Right? Because if I'm adding a multiple of 2 pi, then I'm just doing one more full rotation, and then I get back to the same spot, right? And so that's true for any integer value, n, so that I end up adding multiples of 2 pi. So if n equals to 1, that's going to be 2 pi. If n equals to 2, that makes it 4 pi, or 6 pi, or 8 pi. So I'm adding full circles, full laps to any t value. So this shows how the same outputs are going to be repeated. So it's periodic, right? That's what this is driving at. When we draw one complete graph of sine from 0 to 2 pi, and then we want to move on beyond the 2 pi, then it's just going to be the same outputs, and so it'll be periodic. Good, 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 good. Sort of, kind of, maybe. Okay, so, and looking at their graphs. Okay, well, we have some rough, we can do a rough sketch by looking at all the simple values we know how to find, right? We know how to find, turning this into degrees. Let's zoom in a little here. We've been working with all of these already. So these are values we can easily find by hand. This is 30 degrees. This is 60 degrees. This one's 90 degrees. We also know 45 degrees that's missing in here. But okay, but we can keep going, right? And this is equal to 180 degrees. This is 1630. This is equal to 150 degrees, I think. So this is equal to 120 degrees. Right, so we can find all of these values fairly easily. So we have a bunch of points that we can graph already. So if we graph those individual points, we start to see the general shape of the graph. And let's put it in degrees. And let's create a table. Sine x. So at 0 degrees, the x coordinate, I'm sorry, the y coordinate at that point is equal to 0. Okay, so then we know some basic ones. 30, 45, 60. Okay, so now let's come up with a good way of getting this thing. So let's make the x-axis go from negative 100 to positive 400. And let's make the y-axis go from negative 1.5 to positive 1.5. Okay, so that should give us the results. Okay, so we have all these ordered pairs. 0, 0, 30 degrees, comma 1/2, 45 degrees, comma 0.7075, 60 degrees, comma 0.866. Good, so this is root 2 over 2, this is a half, and this is root 3 over 2. Good. Okay, so then we know some other ones. We know 90 degrees, then we can likewise find simple things like 120 degrees, 150 degrees, 180 degrees, 210 degrees, right? So if we just add multiples of 30 degrees, we get to all the ones we know. 230, 240, 270, 300, 330, and then 360. Good. So these are the standard ones, and then we have a couple other ones that we know. We also know so 45, 90, 135, and then 225, and then 315. Good. So by hand, these are all the points that we can find. Good. Okay. And then by using technology, we don't have to restrict ourselves to these points. And when we get to chapter 7, we find that there's going to be ways that we can find some other ones. So I can find 15 degrees because I can subtract these two, and I can take 15 degrees and add it to 90, and then I get 105, so I can find 105. And so adding and subtracting different angles can get me to different values, but still we can use technology to find many other results. So say 5, 15, 23, 30, 43, 58, right? So I can find other values, and as I continue to fill in all these blanks here, we start to see the general shape of the sine function. So after a whole lot of work, maybe it becomes easy to convince people that this graph looks like this. Any questions? So here's the sine graph. It starts off at 0 degrees, comes up and hits its maximum at 90 degrees. It hits 1, comes back down to 0 at 180 degrees, goes all the way down to negative 1 at 270 degrees, and then goes back up to 0 at 360 degrees. There's a nice graphic for that I found over here. Not that one. Let's work with not that one. This one. Okay, so here's another nice little graphic to show the graph of sine. Remember that we're working on the unit circle, and by chapter 5 definitions, we're really just looking at the ordered pair that happens to be on the unit circle, and then the y-coordinate is the sine function. So at this point, the y-coordinate is 0, right? This is the point 1, 0. So we get this point right there at 0. Now, as we increase that angle a little bit and go this way, say at this point, as we trace this up, as this point goes this way, we're keeping track of the y values, right? The y values is this distance, this height of the triangle. So the height here starts off at 0. Can I touch this thing? Am I allowed to move this? No, I'm not. Okay, so the height starts off at 0. There. There. Starts off at 0, and then slowly the height gets bigger and 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 bigger. Right? So that's where we're tracing this. It goes up higher and higher and higher and higher. And it's going to go all the way until it reaches a value of 1. Let me zoom out a little bit here. Come on. There. Let me start that again. So we start off there at 0, and it traces up to a height of 1, right? Keeping track of this height of this triangle. It reaches its maximum value there at 1, and then as I go past 90 degrees, the height is going to get smaller and smaller and smaller. Still positive though. This y value is still positive, all the way until I get to 180 degrees. And then it starts to become a little negative, small negative, bigger negative, bigger negative, bigger negative, all the way until I reach 270 degrees, and it reaches -1. And then it traces back, and it gets a smaller negative, smaller negative, smaller negative until I get back to 0. So this is at 360 degrees. And now we start to see the periodic part of this thing, because now as I continue to trace past the 360 degrees, I'm going to get the exact same points along the curvature, so therefore the picture begins to repeat itself. Good. So as I go past 360, I'm still keeping track of the height of this triangle, right, which is equivalent to saying the y-coordinate of the terminal point there, P, and so it starts to repeat itself. Good. Any questions, any questions, any questions, any questions? Let me zoom out a little bit more, and we'll repeat it and retrace it for a larger value. So now if I start repeating this, you see it starts to oscillate. So if I go back to -720 degrees, it repeats and repeats and repeats and repeats and repeats and repeats and repeats. Good. So this just keeps going and going and going and going and continues to repeat itself. Good. Which is the same as this function, except this one it's got no bounds. That one was bounded by -720 degrees to +720 degrees, whereas this one doesn't know any bound, right? It just keeps going forever and ever and ever and ever and ever. This is angle 50,000. Good. Any questions, any questions, any questions, any questions? No? No, no, no. Okay, similar thing happens when we look at cosine. Let's zoom in again and look at the cosine function. So now just focusing on the cosine function, let's bring this back down to close to 0. Come on. Not the sine, but now we want to keep track of the cosine. Come on. Okay, so now remember the cosine is the x-coordinate of the ordered pair, so it can also be the distance along the x-axis to that point P, and so if we keep track of that, it starts off at 1, right? It starts up here, and then as I trace across, the x-coordinate, the distance across this way, becomes starts off at 1, and then it becomes smaller and smaller and smaller and smaller until it reaches a distance of 0. Right? And it reaches a distance of 0 when we reach 90 degrees. And then as we keep going past that, it turns into the negative side. The distance x, right? If I drop a little line here and make a triangle, the distance becomes a small negative, and then that becomes a bigger negative and a bigger negative and a bigger negative all the way until I reach the largest it'll reach will be -1 at 180 degrees. So at 180 degrees, the cosine value equals to -1. Then if I move past that, and again keeping track of the x, I still have a negative value, but the negative gets smaller and smaller and smaller until it reaches back up to 0 at 270 degrees. and then the x becomes a small positive, right? If I put a little line, drop it down here and look at the triangle, the base of that triangle, the x-coordinate, is a small positive, and it gets bigger and bigger and bigger and bigger until we get to 360 degrees and complete one period of the cosine function. Questions, 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 questions? Right? And then from that point on, just like the sine function, it begins to repeat itself. We get all the same outputs of the cosine function, so the graph begins to be periodic. It shows that it's periodic. So we can go from there and trace it all the way back to here and retrace it all the way here. Any questions? So one period of the cosine function starts here, comes back down, comes back up there, goes back up there, and that's one period, and then it begins to repeat itself. So over on the Desmos, I can do the same thing. I could create a table. I can find values of all of these for cosine. Cosine x. And I get all those values. Let's put them in red. And if I keep going and find more values, eventually I end up with cosine x. Right, so here's my cosine function. Any questions, any questions, any questions? No, 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 no. Okay, last one. Let's look at tangent. So the tangent function, let's zoom in a little bit. Okay, so remember that tangent is equal to y over x, sine over cosine. So here, y is 0 over 1, so the tangent function is just going to be 0. And as I move forward this way, if I just kind of go this way, look what's happening with the tangent function. Now it's this divided by this. Good. So as I sort of create this triangle here and divide this height divided by this distance, it'll give me some output. And as I'm moving this way, the numerator is getting bigger and bigger and bigger, and the denominator is getting smaller and smaller and smaller. So the pattern you should remember from fractions is that if we have a denominator that's getting closer and closer and closer to 0, and a numerator that's getting closer and closer to 1, right? The numerator is getting bigger and bigger and bigger, but it's not getting infinitely large. The y travels from 0 all the way up to 1, right? The height. The numerator is going to get closer and closer to 1, whereas the denominator gets really, 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 really close to 0. So when it gets really, really close to 0, it ends up getting infinitely, the output of the fraction becomes infinitely large. Did that make sense? Any questions about that? Just saying that if we have any fractions, so let's say we have 0.8 divided by 0.8. Okay, that's going to be 1. Now the next one, let's say this one becomes 0.9, and now this is 0.02. This numerator, as it approaches 1, and then this denominator, as it approaches, gets infinitely close to 0, like 0.000001, then this can go into that a lot of times. So this thing gets large, very, very large, right? And the closer this goes to 0, the larger this output is going to be. Is that okay? Questions, questions, questions? Okay, so that's what happens here with the tangent function. It just shoots up toward infinity. In this little space right in here, it just shoots up toward infinity. Good. What about back here? value is approaching -1, and the x values are all positive. We start off with 1 over 0. I'm sorry, 0 over 1, which is equal to 0. So we start off with 0. And then as we go in this direction, it's just going to become larger and larger and larger negatives until we reach approximately there. Good. So in this space right here, this is the shape of the tan function that we're getting, like this. Good. So it shoots off toward infinity that way, and it shoots off toward infinity this way. Now, at 90 degrees, remember, tangent is sine over cosine. At 90 degrees, cosine is 0. So at 90 degrees and at -90 degrees, we're dividing by 0, so the tangent function is undefined. There's going to be vertical asymptotes here and here. And then after that, it begins to repeat itself. The pattern begins to repeat itself. Good. And then it repeats itself in the other direction. So typically we only graph one part of the tangent function from -90 to 90, but then it should be understood that it's one period and then it repeats itself. Good. And to really confuse people, very often the tangent function is described by the segment between 0 and 180. So they show you this part of it and then this part of it with an asymptote in the center. And you know, you should be able to deduce that it's the same thing. Is that okay? Questions, questions, questions? See what it looks like on Desmos. So we can do the same thing here. Y equals to tan of x. We see we get that. And then these are in degrees, so I can do the asymptotes. Sorry. X equals to 90 degrees. Put it in red. And done. How about x equals to -90 degrees? Also in red. Dashed? Let's make it dashed. So there you go. So this is one period with vertical asymptotes going from -90 to +90 degrees. And this converges toward that asymptote. And then it repeats itself over here, and then it repeats itself over there, and so on and so forth. Any questions about any of these graphs? No. We're good. Okay, there's some other nice, let's see, did we find any other good ones? It's the same thing that we're just looking at here. This is going to be cosine. So we see that it traces the x-coordinate. This is a nice little one that just kind of repeats itself from 0 to 2 pi. So just keep track of the x-coordinate. So the x-coordinate starts off at 1, it gets smaller and smaller, goes to 0, negative, negative, all the way to -1, smaller negative, down to 0, bigger positive, up to 1, and then it retraces itself. That's what this is doing. What's this one? Animation? Oh. So same thing, it's keeping track of the x-coordinate. Or we can have the sign. So here we're keeping track of the y-coordinate. So it starts off at 0, goes up to a height of 1, and then comes back down to 0, goes down to a -1, goes back up to 0, and so we're tracing the y-coordinates of the y-coordinates of the terminal point along the unit circle. Any questions about these graphs? No. Okay, so Here is the standard period of a sine function with some of the known values that we can figure out by hand. And then the rest of those values, it's assumed that we can either use more sophisticated mathematical tools to figure those out, many of those out, but eventually we'd rather focus or rely on technology to help us find the rest of them. Right? So we have the general shape of it that does this. Good. So one period is from 0 to 2 pi, and then it becomes repetitive, right? Periodic. You can also go into the negatives, don't forget that. And then we have a similar thing for cosine. Here is one period of cosine with all the known values that we know how to do by hand. And then using technology, we can fill in the rest and have a nice complete period of cosine. So here's one period from 0 to 2 pi, and then it becomes periodic, repeats itself beyond that. Good? Questions, 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 questions? No? No? Okay, so next we're going to think about the transformations of sines and cosines and see how various operations will affect our sines and our cosines. I'm going to do it in a slightly different order, so I'm just going to jump to the general formula over here, and we'll just kind of study what each one does. So here are the two general function forms that we're going to be working with. Let's focus on the sine one, and then the cosine one is the same thing. It's just cosine instead of sine. Okay, so let's focus on y equals to a sine of, k x minus b. Now, in this context, this whole thing is inside the sine function, so that might not be clear from here. It's not sine of k times x minus b. It is sine of, and then the product of these two, right? And this is where the angle is x, right? This is the input is this guy. Input angle is there, and then all the other constants, all the other variables are constants. A, k, and the b are constants. A, k, and b are constants. So for example, it might be y equals to 3. Hey, how come they don't have a plus thing here? We're missing one more variable that we can add on to it. There's probably another table somewhere that includes the other constant out here. Let's call it c. It's another constant, c, and c are constants. So for example, we might have something like 3 sine of 4 x minus 2 plus 5. And we want to see how can we do a rough sketch of this graph? How do these values, how do these constants affect our graph? The 3, the 4, the 2, and the 5. How do they affect the standard graph of sine? Good. So let's begin by this outside number here. Just like before, we learned that whenever we add a constant, we either shift the graph up or we shift the graph down, and we can easily use Desmos to see how that works. Let's get rid of all of these guys. Yes, leave. More sine. Oh, boy. Yes, leave. Yes, leave. Okay, so y equals to sine x. So here is my standard sine function, right? And this is in radians because it goes from 0 to a little bit past 6 is one complete period. So that means that it's pretty close to 2 pi, right? And I can tell that this should be 2 pi. A little past 6 is close to 2 pi, 2 point something. Okay, so this is in radians. Here's a period of sine. And what happens if I think of a new function? Oh, let's put it into function notation. So let's say this is f of x is equal to that. So let's define a new function, f of g of x, which is equal to sine of x plus 2. Okay, so this plus 2, what it does is it's going to take your standard sine function and it adds 2 to the output. When the original sine function had an output of 0, we add 2, so we get to 0, 2. When this original sine function had an output of 1, we're going to add 2 to that, and that's going to get us to an output of 3 over here. Right? So g of pi over 2 equals 3, because we add this plus 2 there. Good? Good, good. In fact, notation-wise, we can also come back over here, and instead of writing sine of x plus 2, I can write f of x plus 2. Right? So I'm adding 2 to this function. Nothing special about 2. We can also add 3, or we can add 5. We can also subtract. So minus 1, or minus 2. Right? We keep the exact same shape, though. Right? The same period, the same shape. We just shift the whole thing up or the whole thing down. Good. So that's what we want to say, that the c shifts the function up and down. Good, 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 good. Okay, what about the constant out in front? What does this a do? That's what we want to figure out now. Okay, so what happens if we multiply on the outside of the function by a value a? Let's begin by looking at an a that's bigger than 1. Oh, I know what I want to do. First of all, let's make this a slider. Let's make that plus a. That's a slider. And so that's just some constant out there, and then we can see how that constant out there, adding or subtracting a constant, just makes it shift up and down. Okay, so now let's get back to basics now. Okay, so now let's define some new function, g of x, which is equal to, say, 3 times sine x. So what happens when we multiply it by 3? So here's our new function being multiplied by 3. And notice that we still go through all the same values of 0. Because when the output of sine is 0 times 3, the output is still 0, right? But when the output was 1, and now we're multiplying it by 3, we really get to a new height of 3. Right? It's not the same as adding. Before we were adding everything, but here we're multiplying all the outputs by 3. Right? So whatever this is, its new value is going to be this number times 3 to get to the purple one. Right? So what it does is it stretches. This is considered a vertical stretch. It still has the same length, the same period, the same domain completes one period from 0 to 2 pi. It's just that instead of going up to a height of 1, it goes up to a height of 3, and then down to a depth of negative 3. Good. If I make it 5, then it's just going to exaggerate it even more. Right? So the bigger this is, the more exaggerated and pronounced this goes, but always keeping track that it goes through the points 0, 0, 0 in the same period. Good. On the other hand, if I multiply it by a number that's between 0 and 1, then it's going to slow down its height. Like let's say I make it 0.5, then this only goes up half as tall. It used to go up to 1. The regular sine function goes up to 1, but now I multiply the output, right? All the outputs get halved. So it goes up to a height of half and down to a depth of negative half. It still travels through all the values 0 though. Good. So if I make this even smaller, then it's just gonna compress vertically. Let's make this 0.2. It flattens it out. Good. 0.1. Good, good, good. So in general, and what if it's a negative? What if I multiply this by negative 1? well then all the outputs that used to be positive, right? The red one is the sine function. It used to give me positive outputs between 0 and pi, but now because this new function multiplies everything by -1, these formerly positive values become negative, and now between pi and 2 pi, the original sine function used to give me negative outputs, but now because I'm multiplying by -1, they turn into positive outputs. So all previously positive become negative, all previously negative become positive, so it becomes a reflection about the x-axis. Good? Questions, 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 questions? So I can combine that with multiplying by a number, say that's bigger than -1, like -3, and then it'll do both exaggerated, it'll be a vertical stretch, as well as a reflection about the x-axis. Good. So we have some sense of what this could do. So I can make this the value. You know what? I should have stayed in keeping with the letters from that thing I wrote, C. And what did I write? This one would have been A and C and B and K. All right. So this is A, and I can see what happens, right? As A gets bigger and bigger and bigger and bigger, there's a vertical stretch, bigger and bigger and bigger and bigger vertical stretch, or it goes back down. Now if I multiply it by 0, something weird happens. It just completely flattens out and becomes the x-axis. And then as it becomes a negative, it gives you a reflection about the x-axis, and then there's a vertical compression between 0 and -1. Past -1, there's a vertical stretching that gets bigger and bigger and bigger and bigger and bigger and bigger and bigger. Right? Good. Any questions, any questions, any questions? And as far as notation, I can write A sine x, or I can go back to A times f of x, since f of x was defined up here to be sine. Good. And now I can mix and match them. I can define a new function, w of x, which is equal to A f of x, oops, A f of x plus c. And let's make this a new color. Let's find a fun color. How about blue? Done. Okay, so now I have this new function, and it has an A times f of x plus c, where A is this value, and we know what that's going to do, right? And we know that the c is this value that shifts up and down. Good? So the plus out there shifts up and down, and the multiple in front of it will either stretch it or compress it or do a reflection about the x-axis. Good. And again, notation-wise, I can leave that as an f of x, or I can rewrite this as a sine x in here. Any questions? No, 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 no. Okay, next part. What if I multiply the sine, the argument of the sine function, times some constant? So let's define a new function, I don't know, q of x. Qx equals to sine of, let's say I multiply this by 2x. What did it do? Let's look at it here. In fact, let's look at it in terms of a table. Table. We have x, and let's do, this is sine of 2x. Let's see. Do I want to put it on here? Okay, that's fine. Sine 2x. Okay, remember that this is in radians, so as I type in 0, okay, 0 leads to 0, and then if I do pi divided by 3, I get that, and if I do pi divided by 6, I get that, and if I get like 2 pi divided by 3, I get that, Okay, so I'm tracing my results, and if I type in let's do some more pi's. Pi divided by 5, I get that, and pi divided. You know what? I don't like the fact that I'm doing it in radians. Let me I want to do that part in degrees, but I don't want to mix and match those two. So let me go back to this thing and do it with degrees. X and sine 2x. And I want to put this in degrees for the purposes of this table, which means I want to zoom out here. Oh, well, that's not going to be good. Let's make this negative 100 degrees to positive 400 degrees, and this is negative 1.5 to positive 1.5. Okay, so 0 goes there. Okay, now let's say I want to do 10 degrees, and then I want to do 20 degrees, and 30 degrees, and 40 degrees, and 50 degrees, and 60, 70, 80, 90. Okay, so I'm plugging in different values of my degrees, but notice that as I trace the input values from 0 to 180 degrees, because I'm always multiplying by 2, I've really experienced one full shape, one full period of the sine function. Instead of going from 0 to 360 degrees like I would expect, I've been able to do it in half the time. Y equals to sine x is there. Here is the sine function. It goes from 0 all the way out to 360 degrees. But because I have twice x in here, this multiplication of a 2 causes me to go through my period faster. Right? Every time you input an angle, I'm going to double it. So this is the result of sine 20 degrees, even though I'm inputting 10. And this is the result of sine of 100 degrees, even though I'm plugging in 50. Right? And then this is the result of sine of 240 degrees. So by the time I get to 180, I'm really finding sine of 380 degrees. So I've completed one complete period. Good. So that's what happens when you multiply by a number bigger than 1. You go through your period faster, so you have a compression that happens. Y equals to sine of 2x. It's going to look like that. We complete one period in half the time. We can squeeze in 2 periods in the same space that the normal one does. That's another way of looking at it. We can complete 2 complete periods of sine in the same space that would normally take us to do 1 period under the regular sine function. Any questions about that? Good, 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 good. Maybe, sort of, kind of, maybe, sort of. Okay, well, forget that guy. How about if, on the other hand, we multiply it by 4? If we multiply it by 4, then, oh, I don't want to do. We'll see that we finish the period even faster. Let's go by 5s now. There's 5, 10, 15, 20, 25. Notice that by the time we get to 90 degrees, we will have already completed one period of sine. Right? Again, because we're quadrupling every input value. So when I input 30, I'm really going to find sine of 120. When I input 50, I'm really going to find sine of 200. Good. So by the time I input 90 degrees, I'm really finding sine of 360. So that completes one period. Or we can squeeze in 4 complete periods of sine in the same space where you would normally complete only 1 period of sine. Good, 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 good. Okay, the other direction is, as you would assume, if instead we're doing this, and let me get rid of these things. If instead we're multiplying the argument of the sine function by a number that's between 0 and 1, like let's say that this is, say that this can be multiplied by 0.5, then as I find values, say 10, I'm really going to find sine of 5 degrees, right? Because it's half. Let's see if I can write it as a half. Right? Instead of, I plug in 10, but really I'm going to get sine of 5 degrees. And then I plug in 20, but really I'm going to get sine of 10. And then I plug in 30, but really I'm going to get sine of 15. So as I move on forward and trace my values, I go all the way out to 360 degrees, but because I'm halving it every time, I've really only completed half the period of sine. Right? When I plug in 360 degrees, I half it, so I'm really going to get the output for 180 degrees. So now it's going to require me to go farther out in order to get one complete period of sine. I'm going to have to go out twice as far. I got to go all the way out to 720 degrees to complete one oscillation, one period of the sine function. So now it's the reverse, that two complete sine functions can squeeze in the exact same space that sine of 1/2 x fits in. Any questions about that? The impact of multiplying the argument of the sine function by a constant. That's, well, so far we're only looking at positive constants. Good? Questions? Okay, I was going to do the same thing here, except that it's harder to visualize all of that with radians, and so I kind of gave up on it, so let's give up on that. But now we know, now we're armed with knowledge of what happens when we multiply by a constant. So we see that if we multiply the sine function by 2x, it's going to complete the period twice as fast. Two of these are going to squeeze in to the same space that would normally fit in one sine function. Good. Let's get rid of that. So if instead of a 2, we make this a 3, we oscillate even faster. Complete 3 complete periods in the same space that we would normally do 1. Right? So from 0 to 2 pi, we have 1 period of sine, 2 periods of sine, 3 periods of sine. Right? And then we can get really fun here. Let's make it 5. 5 complete oscillations, or make it 8 complete oscillations, or we can get really crazy, do 18 oscillations, right? So it'll complete its period faster, right? It'll do a horizontal compression when we multiply by a number that's bigger than 1. And then same thing in the other direction, as we saw before. If we multiply this by 0.5, it'll slow it down, it'll stretch it out, it'll take longer to do 1 period of sine. And we can really stretch it out even more, make it 0.4, make it 0.3, you can make it 0.2, you can make it 0.1, right? So here, 0.1, it's so big, look at that, it takes it all the way up to there in order to complete 1 period. This is 1/10. That means that there are 10 complete periods of sine, regular sine, that can be completed in the same space that it would take this function to complete 1 period of sine. Good? Questions? And then, of course, what happens when we multiply the argument of the function by a -1? That becomes a reflection about the y-axis, right? We learned that before. So if we take the regular sine function and we multiply it by a -1, it's a reflection about the y-axis. Now, an interesting thing about the sine function is that it's an odd function. It means that its reflection about the x-axis is equal to its reflection about the y-axis. So when I did this versus before when I did this, so let's do I don't know, r of x, whatever. x equals to negative sine x. This one and this one both look identical. Here is a reflection of the sine function about the x-axis. All of these previously positive become negative. All the previously negative become positive. Okay, now let's do a reflection about the y-axis. Well, it looks exactly the same, right? There used to be the sine function comes this way up here, and so I'm going to move it over there, and then we end up with this part of the graph. And then this moves over here to become this part of the graph, and then we end up getting the exact same image. Good. But multiplying by -1 is a reflection about the y-axis. So armed with all that, we can say that if we let this be some slighter value k, and go back to graphing sine. So the red one is the original sine function, and if k is 1, it just equals to that. But as this becomes bigger and bigger and bigger, then it oscillates more and more and more and more. So there's a compression that happens as k gets bigger and bigger and bigger and bigger. And then as k becomes a value between 0 and 1, it stretches it out. So it's a horizontal stretching until it equals to 0. Sine of 0 is 0, and then it just becomes the y-axis. And then in the other direction, it becomes a small negative value. Then it's a stretch and a reflection about the y-axis until it gets beyond -1, and then it's both a compression and a reflection. Good. Any questions? Any questions? Any questions? Questions? No? Maybe? We're almost there. The last thing we need to do is think about what happens as we subtract or add a constant to the argument of the sine function. So let's just see what the graph looks like. I think we remember from before that that must mean that there is a horizontal shift, right? Sine of x plus, this is in radians, so let's make it +1. So notice what happens. The +1 has shifted my original function to the left by 1 unit. So this used to be 0, so now this moves to -1, 0, right? If I plug in -1 into here, I get sine of 0, which gives me the same output of 0. Good. Questions? This value of 2.13, this is going to be pi minus 1, right? Because remember, pi is this guy here. Pi, this is 3.14. If I take 3.14 minus 1, then I get to this point here. So every one of these points has been shifted to the left by 1 unit. And that's what this +1 does. If I make it +1.2, then it'll shift it a little bit more. 1.3 shifts it a little bit more. 1.4 shifts it a little bit more. And it keeps shifting all the way until I get to, say, close to 3. So how about 2.8? And then eventually, if I get to 3.14-ish, then it looks like all I've done is I've shifted the sine function to the left by pi, which also looks like it's a reflection about the x-axis or a reflection about the y-axis, right? So all those graphs look identical. Any questions about that? Did that make sense? Or should I write that down? Maybe? Let me write that down. So we've seen that if we have so from the graph, we've seen that if I have the sine function and I shift it, it's a reflection. This is a reflection about the x-axis. I'm sorry, reflection about the y-axis. About y-axis. So what this does is Here's the original sine function. It goes up, it comes back down, and comes back this way. So let's say I have this point here, A, B, C, and D. Then as I do a reflection about the y-axis, this will come this way, like this, and come back down this way and go that way. Where this traces over here to A, here is where B goes, and C goes over here, and D is over here somewhere. Right? This is what a reflection about the y-axis would look like. On the other hand, if I had sine of x and I multiply by -1 out here, then this is going to be a reflection about the x-axis. So this is going to be this part. It comes down here. Wow, this is really ugly, but you get the point. This goes this way, this goes this way. So this A travels down here to A, and this thing travels down here to B. This thing travels up here to C, and this guy up here travels to D. So this is a reflection about the x-axis. But as you see, they form the exact same graph, right? As I keep going with this pattern, it's going to go that way. And as I keep going with this pattern, it's going to go that way. So either way, we get the exact same shape, right? That's why we say that sine of -x is equal to -1 times sine of x. And we just saw that all of this was equal to sine of x plus pi. Any questions so far? No? 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 In other words, this x plus pi means that if I take this picture, the regular sine function, that goes like this, and I just do a shift and move every one of these points by pi, I shift everything this way by pi, right, all of these points that way, then I'm going to take this black one, it's going to scoot over here, and I'm going to end up getting the exact same shape. This point is going to move there, this point is going to move there, this point is going to move there, and I'll end up getting the exact same shape. Good? Questions, 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 questions? Okay, so now we are finally ready to look at the general equations for these guys. Now that we have all of that information, we know that this -2 is going to shift the sine function to the right by 2 units. Remember, it's a little counterintuitive. When we see a plus, we move to the left. When we see a minus, we move to the right. So this is going to be right by 2. Okay. This 4 in here, this multiplication of 4 is going to cause you to oscillate faster, right? So this is going to be a horizontal compression, compressed by a multiple of 4. Horizontal compression by multiple of 4. Of 4, right? It'll go through its period faster. Goes through period faster. Right? This 5 is going to go up by 5 units, right? And then this is going to stretch it vertically, a vertical stretch. Vertical stretch. So armed with all that, we have a general idea of what the shape of the sine function of this function will be based on the standard graph of a standard sine function. Does that make sense? Any questions? No? 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 Where did the constant go? What did they do with their constant? Did they put it over here on a separate thing? So there's some nice graphs that the author provides for you, so let's go through some of those. Okay, so I did this in a different order, but now we know that this is going to be the regular cosine function shifted up by 2 units, and that this is going to be the regular cosine function with a reflection about the x-axis, right? We multiply every output of cosine by a -1. It's going to be a reflection about the x-axis. So that's what these are. So the regular cosine function shifted up by 2 units. That means that this height up there should be a 3, and that this depth down here should be a +1. Right? It used to be -1. -1 plus 2 gets you to +1. So the old x-axis, the center of the cosine function, becomes this line over here, which is equal to the line y equals to 2. Good. So this line right here is the line y equals to 2. Any questions, any questions, any questions? This point is pi comma 1. Good. This point is the point 0 comma 3. Good. This point is the point pi over 2 comma 2. Good. Okay, the next one is a reflection about the x-axis. So here's the cosine function, and then its reflection. So this point there travels down to this one. It used to be +1. A reflection across the x-axis means it goes down there. And then a point here travels to there. And of course 0 is 0. And a point there, used to be there, travels there. Good. So this one travels down that way. This one travels down that way. This one travels up to that one. Good. And eventually we get this graph. Good, 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 good. Here's a nice graphic showing you what happens when we multiply by a constant. So if we multiply by 2, there's a vertical stretch, right? The blue one is the regular sine function. So if we multiply the regular sine function times 2, we get this vertical stretch one, the red one. If we multiply it by a half, there's a vertical compression, right? Notice that they all go through 0, 0, 0. All the zeros stay the same. Same thing with, so this is a sine function. Multiply it by 3, we get an even bigger stretch. Multiply it by a half, we get this one. Okay. And then by a negative out in front means that we have both a reflection about the x-axis as well as a stretching, a vertical stretch by a multiple of 3. Good, good, good. Okay, we've covered all that, So we get that picture. Okay, so now we start to think about what happens when we multiply by a constant inside the argument of the function. So we establish that it oscillates faster, goes through its period faster, twice as fast. And then here it slows it down. So instead of completing one period in 2 pi, it completes one period in 4 pi. Here it completes one period in just pi, or it completes 2 periods in 2 pi. Here's a nice graphic showing you different ones. Here we have the red one, which does sine of 2a, sine 2x, so it completes the period in half the time. Then we got regular sine, which completes the period in 2 pi. And then we have this other one that stretches out here, this blue one, which is sine 1/2 x. So it takes it twice as long. And then this one takes it 3 times as long. Good. Horizontal compression or horizontal stretching. And we can mix and match things. So here, the graph of this one is going to be a horizontal compression. It oscillates faster, 3 times as fast. So it'll complete, instead of completing the period in 2 pi, it'll complete the period in 2 pi divided by 3. Or it'll fit in 3 complete cosines in the space of between 0 and 2 pi. And then the 4 means that there is a vertical stretching. So instead of going up to a height of 1, it'll go up to a height of 4. Good. Here, this 1/2 is going to be a horizontal stretching. It'll take it twice as long to complete the period. From 0 to 4 pi, it'll complete one period, or from 0 to 720 degrees, it'll complete one period of sine. The 2 is the vertical stretching, so it'll go up to a height of 1 or down to a depth of -2. Height of 2 down to a depth of -2. And then this minus indicates that there is going to be a reflection about the x-axis. Okay, so let's take a look at those. So here's this one. It completes the periods faster, so there's a horizontal compression. It can squeeze in 3 cosines in the space that it would normally take 1 cosine. So if we go out to 2 pi, we'll see that it completes 3 complete cosines. But it'll complete one in 2 pi divided by 3. So that's where this completes one oscillation, one period of cosine, stretched vertically by a factor of 4. So it goes up to a height of 4, down to a depth of -4. And then the other one looks like, oh, they didn't give you a picture of it? Oh, here. And then the other one is this one. So it gets stretched out horizontally by a factor of 2, so it'll complete the period in 4 pi. Start to notice the formula for it. It's this half here, and it's 2 pi divided by half, whatever constant's there. That's what tells you the period of the graph. And then the 2 means we go up to a height of 2 and a minimum of -2, but then there's a reflection about the x-axis. So sine normally goes up, down, and back up. This time we go down, up, and then back down. Good. Okay, we covered how to add and subtract constants and mix and match the whole thing. So this means that there's going to be a shift to the right by pi over 4. This 2 means that there's going to be a compression horizontally. It'll finish this period faster, twice as fast. So it'll complete one period in pi, from 0 to pi, and then shift it. And then this means that there is a a vertical stretching. Okay, so here's all the little pieces. The amplitude becomes 3. Right, there's a stretch beyond 1 out to 3. Shift it to the right by pi over 4, and the period is completed from 0 to pi. So with all those things, we can sketch together a little picture of approximately what the graph should look like. Good? Questions? When you're asked to do this by hand, you need to graph. One common technique is to figure out the 5 important points. This point, that point, this point. That's 3, 4, and 5. The 5 unique points. And notice that there is some nice patterns that we can take advantage of to find those results, keeping in mind that we know them for the standard sine function. How would they be affected by this new equation? Good. Questions? Okay. And then more of the same. Here's another one. Y equals to 3/4 cosine 2x plus 2 pi over 3. Now be careful, because what we want to do is factor out a 2 first, so that we make sure to rewrite it into our standard form. Is that what they did here? Right, so we factor out a 2 to get it into this form. So we want to say y equals to 3/4 cosine of 2 parentheses x plus, and then we want to factor out a 2, so this is just going to be pi over 3. Right? 2x, 2 pi over 3. And then also we want to rewrite this into the form of cosine 2x minus negative pi over 3 x. And now it fits the form of some constant a cosine of some constant k times x minus b, like this. And then we can see what's happening. So this is going to be a shift. So it's looking at this as plus, so it's minus, or if you rewrite it into this form, then it's equal to this. So it's going to be a shift to the left by pi over 3. Right? So this was the original cosine function, starts here at 0, but we're going to shift it this way by pi over 3. Shift to the left by pi over 3. The 2 is going to be a horizontal compression. It completes the period twice as fast, so it's going to complete it in pi. Instead of 0 to 2 pi, it'll complete it between 0 to pi. So this length across this is going to be pi. Good. And then, so, if you want to find these other values, then it means that half of the period will be completed in pi over 2. That. And then a fourth of the period will be completed in 1/4 pi. And then 3/4 pi, right? So this distance is equal to the distance from here to there should be pi 1/4 pi. The distance from here to there should be half a pi. And the distance from here to there is 3/4 pi. 3 pi over 4. Good. So then if we want to know how that actually turns into these key values along the x-axis, we need to take the starting point, which is negative pi over 3, and add positive 1/4 pi. So negative pi over 3 plus 1/4 pi. If I add those two, we need a common denominator, which is going to be 12. So minus 4 pi over 12 plus 3 pi over 12 gets me to negative pi over 12. Negative pi over 12. And that's how they get this number. Right? That's how I know that 1/4 of the cosine period is completed. It goes through the x-axis there. Good. Now if I just add a distance of 1/4 pi to this one, then I can get to the next important value, which is going to be this one. And then if I add 1/4 pi to that one, I'll get another one that goes to there. Does that make sense? Any questions about that? No? 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 So if you're graphing this by hand, it's important to find those key points. So create a table, and these are your x values. The fact that you write it in this form, we know that we want to start off at negative pi over 3, and I know that that's going to result in 1. And then if I go out a distance of pi over 4, I know that gets me to negative pi over 12. And that's going to result in this point, which is 0. Right? If I go another distance of pi over 4, I get to the next value, negative pi over 12 plus pi over 4. Okay, multiply this by 3 over 3. That's going to be equal to negative pi plus 3 pi over 12. That gets me to 2 pi over 12, which is equal to pi over 6. It's pi over 6, and that's what this point is here, pi over 6. That leads me to negative 1, right, just because I know the general shape of a cosine function. And then finally, the last one, which is going to be to go one more multiple of pi over 4 to get to there. Or I can start there and add pi to it. That's another way I can get to it. Since I add a fourth of a pi, another fourth of a pi, another fourth of a pi. Really, I'm taking this one and I'm going to add pi to it, plus pi. So negative pi over 3 plus pi is going to get me to 2 pi over 3. And that's how we find this number. 2 pi over 3 is the end of my period for cosine, and I know it ends up at 1 because I know the general shape of a cosine function. So these key values along with my understanding of what these numbers do, right? A horizontal compression of factor of 2, this is going to affect the output of my function. So instead of going up to the amplitude of my function, instead of going up to a height of 1, it goes up to a height of 3/4. So that's how I know that this isn't really going to go up to 1, it's going to go up to 3/4. And this isn't going to go down to, wait, oh, I skipped something. I blame you guys. I forgot the other one that goes in here. Correction. Okay, so 2 pi over 3 is this one. And let me erase this. So it's not that it was wrong, I just skipped one. Well, actually, this part is wrong. So this part is this one. So this plus pi gets you to this one. But I've neglected this one, which is going to be pi over 6 plus pi over 4. And that's going to get you to 5 pi over 12. And then that gets you to another 0 here. Right? 1, 2, 3, 4, 5. The 5 key points that trace the sine and the cosine functions. Good. Okay, so back to this thing. The amplitude is affected by this constant out in front, so this becomes negative 3/4, and then this guy again becomes positive 3/4. 0 doesn't get affected. Good. Questions? No? Okay, so when I give you an equation, a really ugly equation, make sure you do a little bit of algebra to make it fit into this form. And there might be like a plus a constant or something out here. And then I might ask you to find the 5 key values that are needed in order to graph or sketch the general shape of the function. So you need to find the new period. This guy will help you find the new period. The period is equal to 2 pi divided by this number. Okay, so in our case, the period was 2 pi divided by 2, which gives us pi. Good. This will tell you whether you add or subtract from the starting value. So here we're going to do a shift to the left by pi over 3. So starting at pi over 3, we're going to add values of our period, right? So we're going to do 1/4 of our period, 1/2 of our period, 3/4 of our period, and then again the full period, and that'll get you to these points. Good. You can also think of it as percentage. 25% of our period, 50% of our period, 75% of our period, and then 100% of our period to get the 5 key points. Good. Once we have the 5 key points, then the outputs just come from our general understanding of the shape of a cosine or a sine function. And then this value out here might affect our output, right? Depending on the amplitude and depending on whether it's positive or negative. Any questions at all? No. Using graphing devices to graph trig functions, well, we've been doing that all along, so that's easy. So practice doing that with your calculator. That's all this is. And the homework will clearly identify which ones are questions that you can use your calculator on or technology to do it. Good. Okay, so you can see you can get lots of cool graphs depending on which function you type in, but there's just no way we'd be able to do all of this by hand, so be careful, pay attention to that little graphing calculator symbol next to the exercise indicating that that's a question that's supposed to be solved with a calculator. Okay, all right, these are just calculator things, and that's pretty much all we need to do for this section. Okay, this is a good place to stop. This is the end of section 5.3. Yeah, 5.3. Are there any questions on anything? No? No? No?